Thanks, Scott, for such a generous introduction. It's the same for me as well. We search for topics, especially like traffic intersections and so on. Like Steve and you guys had done already so much work. We were always be just looking through your papers, looking at what are the things that we could do. So thanks a lot for that nice introduction. Hello, everyone. Hope all of you are keeping safe and doing well. So I'll get started with my talk. So my research is motivated by scenarios where cities and specific domains, specific environments within the cities have to automatically adapt by reallocating resources depending on some regular events, like a Super Bowl event, which is a periodic event which happens. But after that, like if taxis are required, then how do you match which are the ones that have to go there, and how do you plan for that in advance so that whenever the match finishes, there are enough taxis coming there. So the goal is to automatically adapt by matching these resources depending on, it could be regular events or not so common events. There could be some kind of shocks or disturbances to the system, like there's a massive accident on the road, so you have to pull in all your emergency response vehicles at the right locations, to the right locations so that they are available when required. So the research is motivated by such kind of scenarios. So within that context, I'll be talking about some specific works that we have done recently. And this is joint work with students who were with me when this work was done in the last 2 years, but all of them have moved on to bigger, better things. And so Abhinav, Meghna, Sanket, and Tanvi are the students, and then the collaborators are Nesh at SMU, Milind now at Harvard, and Patrick at MIT. Okay, so here are some quick examples of the kind of problems that we have looked at. So taxis, all of us know, like have to be matched to customers continuously in aggregator apps like Uber or Lyft, etc., so as to maximize revenue. And here, there's no matching entity that is present. It's just there's a supply and there's a demand. You are matching supply to demand, but you have to continuously match. Like once a taxi is assigned to a customer, the customer gets dropped off, and then the taxi has to be again matched, and so on and so forth. And similarly, in bike sharing systems, they have to be matched to the right locations. And in this case, there is a truck which moves the bikes over to the right locations, or food delivery optimization. So these are some of the ones where the goal is to maximize revenue, and they're not as safety critical environments. We have also looked at some of the safety critical environments, like allocating ambulances to the right base station so that the response time is minimized, or Coast Guard boats to the right locations, and so on and so forth. So here are some domains. The goal in all of these cases is to sequentially match supply resources to demand, so as to optimize some metric, typically efficiency. It could be in terms of response times in the safety critical environments. It could be just revenue or waiting time, things of that nature. Okay. So the problem statement, the short problem statement is to match supply resources to demand continuously online. There are several challenges to this. The supply resources themselves could be centralized in the sense there is a centralized entity controlling them, or they're all decentralized. There's a separate objective for each agent. Then we have demand uncertainty, because the customers come in when they like, so there is some uncertainty associated with it. But if you have sufficient data, you have some sense of the distribution of the uncertainty. And then we are having to make sequential decisions, that is the matching decisions of assigning taxis to customers or ambulances to base stations and so forth. And the complexity and scale is the final one, because we have to worry about making decisions at city scale. So for instance, in the case of taxis, there are about 30 or 40,000 taxi drivers whom we have to make assignments for. So those are the broad challenges. And this is just to give a sense of the research that that we do. On one side, we have the complexity, which is deterministic, cooperative, deterministic, competitive, then stochastic, cooperative, stochastic, competitive. Cooperative, competitive come in when you have a single objective, a centralized aggregator doing it, or everyone has their own objective. And then on the y-axis, we have scale, small scale and large scale. And our target is to solve these things at the largest scale, while considering all the aspects, which is stochasticity, cooperative, competitive, all that. So that's our goal. That's the area that we want to focus on. Now, what exactly is the trick then? How can we suddenly go ahead and say we are going to solve the largest number of agents with all the complexities involved? So there's a catch there, in the sense that our focus is primarily on urban environments. And the good thing about urban environments is that, especially the kind of domains that I mentioned, is that these supply and demand entities, they don't have, so there's anonymity in the matches. That is, it doesn't matter which taxi you match to which customer. From each other's perspective, who is assigned to who doesn't matter. So there is what we refer to as anonymity in the matches. And there is also a lack of identity to the individual supply and demand resources. So these aspects help us do these matchings at a large scale. So we exploit those properties in the different problems we look at, and those help us achieve the scale we want, while considering all these, the stochasticity and the cooperation or competition that is present. And there are other properties as well, which we have exploited of these domains, which includes factoredness and being able to aggregate or abstract out supply or demand resources, right? So these are the main properties that we exploit at a very high level. And it's been definitely made easy because of the availability of data. In Singapore, one of the good things is that it's easier to approach the different entities, and most of the time they're willing to try out. So we've had real world data sets related to taxi fleets from 2 companies. We have had emergency response data sets, bike sharing, traffic patrols, theme park, and so on. So we have worked on all these different data sets. And because we have access to this data, we have some sense of the demand distribution. And other than publishing this research, we have also built a few systems which have been deployed over the years. One of them is the ambulance allocation optimization. So this has been taken by our Singapore Civil Defense Force, who use it to position their ambulances, and similarly Coast Guard in Singapore. And our taxi guidance system was actually implemented with the Land Transport Authority, where we were given access to all the data coming in live, and we had to provide guidance to 500 of the selected drivers to showcase whether our system can improve the idle time, because most of the taxis, normal taxis, not the Grab, not the Ubers and the Lyfts, but normal taxis, can we reduce their idle time and move them to right locations at the right times without having someone book the taxi. And similarly, we have also, and we were able to improve that by about 27%. Similarly, in vehicle pooling or sharing, we have been able to come up with an approach which which has some really good results, which I'll briefly talk about. So these 5 slides are meant to give a high-level overview of the kind of work that we do. And the main theme that I'll focus on, which is some of the main work that we have done in the last 2 years, has been on reinforcement learning with operational constraints, because most of these are online problems and we have to keep making decisions on the fly as you get these booking requests and so forth. So how do we do that? And I'll talk about a few areas, give a high-level overview of our approach, and in some cases, I'll go into a little bit more detail. The first one I will talk about is real-time ride pooling. So this will be like Uber pool and so forth. How do we do this kind of ride pooling? So what happens if all of you have heard of this, then it's okay. If not, let me just quickly go through the scenario here. So at each round, what we have is we observe incoming demand. Each round would be like maybe 30 seconds or a minute. And then we observe incoming demand. It could be a single ride request or a batch of ride requests. And we have to match demand with supply. That is, we have to match multiple of these requests that have come in, demand requests that have come in, to individual vehicles, while satisfying constraints. For instance, that if you go directly, if it takes 10 minutes, then it can be more than 15 minutes for a ride pool request. And the pickup should not take more than 10 minutes, things like that. So these are some of the constraints the companies use to ensure there is certain level of quality of service that is met. So the customers then, will provide like what is their source and destination, and then there's a price given, and what's the rough drop-off time based on the allocation that is provided to them. Okay, so and the objective here is to maximize the total reward over certain number of rounds, right? So typically, most of these matches existing work. So most of the existing work focused on myopic approaches, which is they look at what taxis are available closest to the customer, and they make a match. Now, why is this a challenging problem? Why is it interesting? So typically, if you just have the single capacity match, then each taxi has to be matched to one customer. So it's your standard bipartite matching problem. So that is that's the first figure over here. But when we have multi-capacity vehicles, what happens is that we have to match each taxi to a combination of requests. And the interesting thing here is that then it's no longer a bipartite matching problem. It's matching on a tripartite graph. All right, so you have your taxis. The taxis have to be matched to combinations of requests, and these combinations have to be such that a request can only be part of one combination at any time. It can't be part of two combinations. So because of these conditions across two different sets of edges, this becomes a lot more complex. And given that we have to make quick decisions on the fly, that's why it becomes an interesting challenge. And do note that we want to consider the fact that whatever matches we make will have an impact on the matches we can make in the future. Because if you allocate it to the wrong request, the taxi could be going to locations which are very far away from the main center of the city, for instance. So that's why it's a challenging problem and an interesting problem. So the existing work, as I was mentioning, most of it is in the myopic space. They maximize the number of requests served in that time step. And there's a heuristic way of generating these request combinations. So if you have 20 requests, the way the requests are generated is that some of the smaller combinations are generated exhaustively, and then later requests are not exhaustively added, but based on whichever are feasible, they get added. So there's a DP-based algorithm which is not as complex in the sense you can generate these request combinations on the fly. And our contributions have been in the non-myopic space. That is, we want to not just focus on the immediate set of requests that you have, but also focus on the kind of requests that we can get. Primarily because we have data. We have lots of data, so we want to use that data to figure out what are the kind of requests we're going to get in the future, and use that to plan. Okay, so the contribution, our first contribution is this neural approximate dynamic programming approach. The overall flow of this is that of the overall problem that we have is that we get requests, and the requests from the requests we generate all the feasible trips. That is, if you have two requests A and B, those are there's a combination or a trip which does not include any of the requests, and then there is a trip which includes one request, and that request can be A or B and then AB, and then those combinations have to be matched to the taxis that we have. But the first step is to just generate all these trip combinations, and then without our contributions, that is the pink boxes here, the way things get done is after the feasible trips are generated, then there is an assignment that happens according to the ILP. That's the integer linear program. There's an MIP, there's an ILP which gets run, and it's sufficiently small that you can solve this for when the capacity of the vehicles is smaller. So you can solve it very quickly and get an allocation, and then you simulate the motion, meaning you make the assignment, the taxis go ahead and drop off, and then the same thing continues. Now, our key contributions, the first of which is to score these feasible trips, in the sense that we want to understand how much value is for a taxi to take on this request or take on this request combination. Given its current location, if it takes on this request combination, what is the value of that? We want to, over time, by simulating based on past data, we want to learn the value of a taxi and vehicle combination. And the good thing here is that a taxi can be identified just based on its location, where it is at right now. And then the request can be, or a request combination can be identified based on their locations as well. So this can be a general enough, it can be learned without having specific identities associated with the taxis and the requests. And once we have done that, once we have scored feasible trips, we modify the ILP slightly because we want to maximize the score of the combination that we have assigned. So there is a little bit more input that comes in. And once we assign according to the ILP, then we use this as feedback in the sense that based on which of the requests were assigned, we look at that, because the ILP is not getting captured within the scoring mechanism or within our action mechanism. So after the assignment is made and it is executed, after the assignment is made, we take that into consideration that this taxi was assigned to this customer. So that gets some amount of reward. So that is used to update the score function, and then it gets simulated. And the key place where approximate dynamic programming comes is because we have these demand requests or the stochasticity in the environment that is not dependent on uh, actions of the taxi drivers. The stochasticity that is present is external to the system. And therefore, we can use an ADP kind of mechanism where we just have to learn the value of the state using a neural network. So that's why we refer to this as neural approximate dynamic programming. And we were able to get some very interesting results, which were a lot better than the existing best method. We have this, so the first of which was a public data set, the New York data set. And the second one is an extensive data set here in Singapore. And the way the maps are represented are according to the intersections that are there. So the entire map of the city that we are working with is used. And the requests come in according to the data set. And we control the number of taxis just to evaluate the performance of our approach. And in this case, NeurADP was trained using 8 days of data. This is the neural ADP approach. We also have another approach, which I didn't talk about. It uses requests from past 10 days and it uses future demand samples. So this is more of an MIP-based approach. It's a stochastic optimization approach. So it has a request from past 10 days and it uses future demand samples and solves this stochastic optimization problem to create assignments. And what we were able to see was our approaches were able to provide, in some cases, up to 14.7%. And in other cases, also the improvement. So in this graph here, what we have is the capacity that is changing. 2, 4, 10. Our approaches are scalable irrespective of the capacity, or at least until a capacity of 10, we didn't face any issues. And within the constraints that are present for pickup time window and drop-off time window, we are able to make these assignments within 60 seconds. And this is on like academic machines, not commercial machines. So we are able to generate the allocations and everything within 60 seconds. Yeah. So this was one of the first contributions that we had. I will, and then even in the second data set, which is a bigger data set, we got about 6% or so. And just to give a sense of the magnitude of this improvement, typically in taxi companies, even or even one of the aggregator companies here referred to as Grab, for them, even an improvement of 0.5% is considered as a big improvement. And these results here, we have a lot of results in our papers here. I'm just showing the main ones, but these are significant, statistically significant improvements, and we were able to really get quite high numbers compared to what is considered a good improvement. Okay, then we'll talk about the second contribution. This is on online ambulance allocation. The idea here, so first let me briefly explain the setup of the ambulance allocation problem. So typically in cities, there is, these emergency response systems are owned by the governments themselves. But essentially you have a set of ambulances and there are a set of base stations where these ambulances are situated. And the goal is to allocate ambulances to base stations in such a way that the response time or the time taken to serve a request is within some threshold. That's the typical objective. And here here we are considering a specific kind of scenario where there are unpredictable surges, like a big accident happens, or there's unexpected traffic jams because of, I don't know, one of the things that happened here in Singapore was a big metro breakdown. So pretty much the entire center of the city was clogged, or with terrorist incidents and so on. So when that kind of unpredictable events happen, how do you adapt your resource allocations so that um, so that you minimize or you are able to satisfy that condition that incidents are responded to within a certain number of minutes. So that's the problem that we are considering. The key change from a traditional or the one other key thing that we have to worry about here is that there are constraints. The constraints here being that we have to worry about the capacity of the base station, and there are more operational constraints which say like this area of the city has to have at least so many ambulances. Overall, this region should have these many ambulances and so on. So there are those kinds of constraints that the city, the agencies decide based on what's the population demographic and how many people live there. So some of these are determined by the agency, and these constraints have to be met when we are changing the allocations. So the model that we have chosen to represent for this is reinforcement learning. We could have also tried online allocation, but because when we have to solve this big MIP online, it can take a lot of time. Unlike the taxi case where the MIP is a much easier and simpler one, here the MIP, if you write it down, is quite big because you have to make assignments across all these different resources and base stations. That's a bit more complex one because ambulances have to be dispatched to incidents, and then once you dispatch to incidents, once you dispatch the ambulances to incidents, the ambulances take the patient or the victim to the hospital and then return back and so on. So you have this kind of route thing also has to be captured. So therefore, the MIP that is required to solve this is much more complex. So doing this doing this online by solving an MIP is not feasible. So that's why we went ahead and proposed an RL-based model. The issue though there is that the number of actions that we have in this case is very, very large. Because if you have about 50 base stations and about 70 or 80 ambulances, then the number of combinations is just way too many. And the other thing is that in case of RL, in case of this problem, there are constraints on action space. So there's some amount of work that was done in this space. So there was work in deep reinforcement learning in large discrete action spaces. The main drawback of this one, even though it works with large discrete action spaces, is that it is not designed to handle constraints. And then there's the constrained optimization for deep reinforcement learning. This is the closest piece of work. Unfortunately, the thing is that it works for general constraints. So it's the approach itself is not very scalable. With the number of constraints we have and with the number of resources we have, it's very hard for this kind of approach to scale. And we did also do experiments with this approach on smaller scale problems. So that's where our main contribution is. We introduced this resource constrained RL problem, um, uh, where you have your states, actions, and so on, but there are also resource constraints on action space, one of which is the global sum constraint, which is that um, the at any point, the overall allocation should be equivalent to the total number of ambulances. So if we convert this action space into like a continuous thing where the proportion of the total ambulances is your action space, then the overall sum has to be limited. Scott, till when do I have? Is it until
I think it's 49
9:15
minutes. So
or
you should have until
5 more
like
minutes?
you should have 10 more minutes roughly,
10 more minutes. Okay.
and then we have questions.
Okay. Yeah. So one of the first kind of constraint is this global sum constraint, where the sum of all the actions is a fixed entity, and then you have local minimum and maximum bounds, which is uh, for each of the base station, the number of ambulances that you assign is limited. And then you have regional hierarchy in the sense that like in a district you have X number of ambulances, or in a city you should have at most these many number of ambulances, or at the entire state level you can have these many number of ambulances. So it's more of a hierarchical constraint wherein you put constraint on abstracted entities. Um, and these are constraints that we did not make up. These are things that are used by these emergency response agencies. Um, and so that was the problem setup. And the approach we use, because we convert the action space into into continuous space, just to avoid having to deal with very large discrete action spaces. In this case, because it's a resource allocation problem with the summing to one, we could convert the action space into a continuous action space, and then we can use this DDPG approach, deep deterministic policy gradient, and we combine it with this opt, which is wherein you have a neural network where there's a constraint enforcement layer within the within that neural network, which ensures that the output that you get out of the neural network is always satisfying those constraints. Our key contribution in this case is the algorithm. It's a generic algorithm which works for any kind of optimization problem, as long as it's a continuous optimization. It's a linear it's a quadratic optimization. It works. It doesn't place any restriction on the kind of constraints that are required. But in our case, we do have specific kind of constraints. We have the summation constraint, we have this lower upper bound constraint, and we have these hierarchical constraints. For such constraint, or in our specific setup, we don't really have to have the nearest, we don't really need to have the optimal possible answer. We can also work with a solution which is which satisfies all the constraints. So it's satisfaction versus optimization. And when you pose the problem that way, you can still use the insights that this Approximate paper had proposed, but we could come up with a way to not having to solve that entire optimization problem. Instead, you can provide a message passing algorithm wherein we generate one feasible solution and then make modifications to it until it satisfies all the constraints. And this is a very simple process. It's an iterative method which computes the solution very quickly. And yeah, and we were able to include it within the context of this DDPG algorithm, and we were able to quickly. Uh, sorry. Yeah, so we tried this on multiple problems. These approaches, we looked at a normal demand pattern that is there, which is based on the past data, and then we have random surges with certain amplitude uh, that is how intense it is, and also the duration of the surge. So we simulated this. So this was, we couldn't find anything in the data which was representative of a surge, but we could simulate these things just to see how the approach would adapt. And we compared against a greedy baseline approach, because in these in emergency response, typically such kind of greedy baselines usually work really well. And we also looked at another setting of bike sharing, where we just have real data. The interesting thing about bike sharing is that there's a lot of uncertainty there. There's a lot of oscillation in demand, and there's a lot of variance there. So that's why we took that data set and we compared against one of the existing methods. And in the case of ambulance domain, when the demand is normal, there's no point. I mean, we do not get any improvement. It's roughly the same as what the baseline greedy method does, maybe even slightly lower. But on the other hand, when there is a surge, within that surge duration, or within a few days of the surge duration, if you look at the difference in the performance, there's a huge improvement that we get. So in this case, this violet bar is our approach, and yeah, so that works really well. And in this case, higher is better. And in case of yeah, so there was about 15% improvement over the greedy baseline. And then we have the bike sharing domain. In this case, lower is better. And compared to the existing method, our main DDPG Approximate method was able to achieve quite a significant improvement over this kind of more static optimization method. So I have one last thing I'll quickly go over. This is one of the final ones where you have, so we refer to these as threat screening games. This is under the category of individual objectives. So we are no longer trying to optimize for an aggregated thing, but individual objective. I didn't go into the taxi ride one. I'll just briefly explain this threat screening games, and then I'll stop here. The idea here is that we have to make online decisions on the resource to use for screening a passenger. At airports, at land ports, and so on, the personnel there, they have to decide which resource is used for which person. And usually the way it is done is based on the location where that luggage is going or where that person is going, and then we have to figure out which resource to use for which customer. Typically, static approaches were used for such cases. Security games-based approaches were used previously. The method that we propose in such cases, again, is one of RL with a constraint on risk of missing a threat. We were able to once again come up with a mechanism where this optimization that we have to perform is within the deep network, so as to ensure that this constraint of risk of missing a threat is satisfied. And by doing that, we are able to ensure that we're able to make these assessments on the fly because it's an online decision without having to solve a big MIP, and while satisfying the requirement on the risk. So with that, I will quickly, I'll stop here. These are some of our main results on online sequential matching over the last 3 years. And yeah, I'll stop here and happy to take questions.